Alright guys, starting back where we left off on heating curves. So first off with heating curves, again, what we're talking about is this guy right here. Okay, a couple things we need to know. We've already talked about what melting point boiling point is, and in terms of ATMs being at 1 ATM, we talked about a little bit about the different points that we need to recognize on the heating curve, but let's talk about how we solve these problems, because this is where the math is coming from in this chapter. So first and foremost, we have this term enthalpy. Those of you that took AP Bio, you probably recognize that term. This is also called heat, and it is dealing with energy. So we have the enthalpy of vaporization, or we have the heat of vaporization. Both are interchangeable. So the other thing this can be is delta H, H coming from heat, and then it would have a VAP after it, which stands for the delta H of vaporization. Okay, and what this actually is, it's the amount of energy required to vaporize 1 mole of a liquid at a pressure of 1 ATM. Okay, or vice versa, it could also be the amount of energy released to condense 1 mole of a liquid at a pressure of 1 ATM. Okay, we have the delta H of fusion, or the heat of fusion, or the enthalpy of fusion, whatever you want to call it, which is the change of energy that is required to, basically this should be the same definition as this up here. Only difference is melting 1 mole of a solid at 1 ATM, or again the amount of energy released to freeze 1 mole of a solid at 1 ATM. Okay, so these two values would be on the flat point. So if we think about our heating curve being something like that, you would have delta H of vaporization down here, and delta H of, actually, excuse me, try that again. Alright, sorry, delta H of fusion would be down here because that is our melting, freezing. There we go. And then delta H of vaporization would be up here because this is our boiling, condensing, going from liquid to gas. Okay. We then have this thing called specific heat capacity. And I don't know if that's something, a term you guys have ever heard before of, but basically specific heat capacity is how much energy is actually absorbed by a substance, and then the temperature change we see from that amount of energy. So something that has high specific heat capacity, such as water, okay, it's going to absorb energy, like everything's going to absorb energy, but we're not going to see a big temperature change in due to that energy absorption. In other words, temperature is proportional to kinetic energy. Kinetic energy is the motion of the molecules. As it's absorbing energy, it's not producing a huge kinetic energy change, therefore we don't see a huge temperature change. Versus something like, let's say, a metal. And a metal, you know, heats up and cools down very readily. If you hold a penny in your hand, it's going to heat up. You put it down, it's going to cool down very, very quickly in both cases. That is because as it absorbs energy, it transfers that into kinetic energy a lot quicker, and therefore we see a lot quicker temperature change due to that absorption of energy. And we have an equation for that, which we're going to talk about this a lot more in the next chapter as well, but we're going to use it for right now, which is Q, which is energy. Also related to heat, which we'll talk about in the next chapter, equals M, lowercase m, which is mass in grams, okay, times C, specific heat capacity. This is a constant for each individual substance at each individual phase. So this is what I was talking about with the verticals on these can have different slopes because of how each phase absorbs energy, and how well it absorbs energy. And then delta T is our change in temperature. Okay, and this could be either Celsius or Kelvin because it's a delta, it's a change. Hopefully we know this triangle means delta. I don't know if that's something we've talked about yet or not, but we'll see that a lot over the next couple chapters. Delta means change, so meaning if we start at, let's say, 0 degrees Celsius and go to 150 degrees Celsius, our change in temperature is 150, and that change would be the same whether it was in Kelvin or in Celsius. Okay, so that's specific heat capacity. And again, specific heat capacity is important because it's recognizing that different substances in different phases will absorb temperature different, or will absorb energy and transfer that into kinetic energy, therefore measured in temperature, differently. Okay? So again, looking at phase change diagram, where do we use these pieces? So we already talked about delta H of fusion is on the first flat mark as we're fusing it basically, or melting it, freezing or melting. Our vaporization, delta H is up here, which is either boiling or boiling or condensing one way or the other. And then our MCAT, as some of my students call it, MCAT, or Q equals MCAT, or delta T, I should say, is on any of these horizontal lines. And the reason being is because we actually have a change in temperature on these vertical lines, excuse me, not horizontal, these vertical lines. We actually have a change in temperature. So we can't use Q equals MC delta T on our horizontals because we don't see a change in temperature. And also remember what's going on. On our verticals, temperature is changing because energy is being absorbed and turned into kinetic energy. Down here on our horizontals, energy is being used to break intermolecular forces. So two different processes and therefore two different equations that we have to use. Now, what all does this mean? How do we use this? What do we do with this? It's actually fairly straightforward. It's just a lot of math, but don't get too overwhelmed. So let's say this is our question. How many kilojoules are needed to raise the temperature of 112 grams of ice at negative 18 degrees Celsius to steam at 109 degrees Celsius? So first off, what are we looking at here? We're looking at energy to heat up water, specifically, okay? And where we're starting is looking at this. We're starting somewhere down here below or in the solid line, which is our negative 18. I'm just going to draw that at some random place. It doesn't really matter where that is. And we're going all the way up here to 109. Okay? And then what we have to recognize is each change of direction, so we're going up and then going flat, going up, going flat, going up, is going to be a different equation because, again, different processes are occurring and therefore different considerations have to be taken, okay? So what we have to recognize is we're heating up the solid. It's going to absorb energy differently, okay? So the change in temperature here is going to relate to the amount of energy actually absorbed. Delta heat of fusion is how much energy required to break the intermolecular forces here. We are going to have the amount of energy to go from 0 degrees Celsius to 100 degrees Celsius here. And I'll tell you where I'm getting those temperatures from in just a moment, which again, because this is a liquid, it's going to absorb energy differently. It's going to have a different heat capacity, C, than our solid, because it is a different type of substance with a little bit more mobility. Okay, and then we have our energy to break all the intermolecular forces here. And then we have the amount of energy of gas to increase it from 100 to 109. So where am I getting these numbers from? Well, these flat lines are phase changes, and I'm dealing with water. And the reason I know I'm dealing with water is because it tells me ice and steam. Okay, you are not always dealing with water, but that is kind of one of the common ones. It's easy to use, but it can be anything, so keep that in mind. So one of the questions I've seen on College Board is benzene. Well, benzene's not water, therefore it's got a different melting point and a boiling point, and etc. So just kind of keep that in mind. This just happens to be the case because we're dealing with water, that we automatically know its normal freezing point is 0 degrees Celsius and its normal boiling point is 100 degrees Celsius. Okay. From there, we're given all this wonderful data. Okay. We're told the specific heat capacity of ice is 2.087. Specific heat capacity of water is 4.184. Specific capacity of steam is about 1.996 joules per gram degrees Celsius. Okay, so these are specific capacities used at each different place. Okay, from there we're given our heat of fusions to our enthalpies. There's the word I'm looking for. Sorry, our enthalpy of fusion is 6.02 kilograms per mole, and our enthalpy of vaporization is 40.7 kilojoules per mole. Notice the difference in this number here. It's only about 6 kilojoules per mole to go from a liquid or solid to a liquid, but it's 40 kilojoules per mole to go from a liquid to a gas. Why is there such a difference there? Again, it comes down to the amount of intermolecular forces that are breaking. So at the fusion, we're only breaking a few. At the vaporization, we're breaking a whole lot. We're breaking all the ones that are left over. So again, we have a big difference in number there. Okay, so let's talk a little bit about how we do this. First off, we have to recognize again, each direction change up here results in a different mathematical problem. Once we get done with all of them, we have to add them up. Keep in mind, we have joules for our MCAT equation, our Q equals MC. I'm writing G again. Q equals MC delta T. Okay, those are all going to be in joules. And over here, we're going to have kilojoules. So when we add them up, we have to pay attention to the fact that they are in different units. Okay, so again, up here, I have problem 1 going from negative 18 to 0 degrees Celsius. So that's my first equation. I have 0 degrees Celsius to 0 degrees Celsius. That's our melting. That will be a second equation. 0 to 100 degrees will be a third equation. 100 to 100 will be our fourth. And then 100 to 109 will be our fifth. You won't always have that many, so don't panic. I'm doing a full-blown one so you can kind of see all the different pieces and how it works together. So let's go through. First one we're going to do is the negative 18 to 100. And I'm using my MCAT here because I've got my vertical line. Okay, and I'm changing temperature. So let's kind of go through and think about this. So problem 1 is a Q equals MC delta T, where we have mass was given in the original problem. So let's go back up here and grab that. We're told it's 112 grams of ice. So 112 grams of ice. We have specific heat capacity of ice is 2.087 joules per gram degree Celsius. And our change in temperature here is negative 18 to 0. So we're only going from one spot to that first change in direction. So negative 18 to 0 is going to be a change in temperature of 18 degrees Celsius. And we find change in temperature, by the way, as temperature final minus temperature initial. It's always final minus initial. So final is 0 minus negative 18, which is where I'm getting a positive 18 change in temperature, just so you have that basic idea. So calculate Q. Q is going to be equal 112 times 2.087 times a change in temperature of 18 degrees Celsius. And I should be writing units. So we have grams times joules per gram degrees Celsius times degrees Celsius. Okay, and that's going to give us a Q1, and I'm calling it Q1 because it's my first step, with proper sig figs. In this case, technically this is 18.0, so it should be 3 sig figs because we have 3 in our mass, 3 in our change in temperature of 4210 joules, or we can go ahead and convert that into kilojoules. Either way, I'm going to go ahead and do that, 4.21 kilojoules. Okay, and the reason it's joules, check this out. Joules per gram degree Celsius. Grams is on the bottom, grams is on top here. They cancel out. Celsius on top, Celsius on bottom, cancel out. We're left with joules. Okay, so now we do the next step, which is going from 0 to 0. So it says horizontal here. Whoops. Don't know why it keeps doing that. I scroll up and it wants to scroll back down. So it says horizontal going from 0 to 0, and we're melting, okay, which means we use our delta H of fusion, which is 6.02 kilojoules per mole. So notice here's moles, not grams. So kind of the way we can think about it here is delta H is equal to energy over moles. Okay, what we're trying to do is calculate the amount of energy required here if you want to set it up like this, or you can set it up using train tracks. Either way works. It's kind of up to you. The first thing we need to do is get our moles into grams, and I can show you both ways. So 112 grams of H2O is going to be converted into moles, which is 18.02 grams per 1 mole. Okay, and that's going to give us, again, 3 proper sig figs, 6.22 moles. Okay, so again, 2 ways we can do this. We can do 6.22 moles in our train tracks and set it up as 6.02 kilojoules per 1 mole, which is basically using this guy as a conversion factor. Or we can set it up using the equation as 6.02 is equal to the amount of energy we're trying to find over our moles, which is 6.22. So notice both times you're calculating, you're multiplying the 6.22 times your 6.02. So it doesn't really matter which one you do, just kind of pick and go with it. Either way, what we come up with is the energy here, which I'm just going to call E2, but it's also Q2. Both of these energies are going to be added together so they can be the same unit, or the same letter if we want to. Okay, and that's going to give us 37.4 kilojoules. So notice a lot more energy required here than what's required here. 2 reasons for this. First off, we're only changing the temperature by 18 degrees Celsius. Second off, down here, we're not changing temperature, but we're breaking into molecular forces, which does require a lot more energy than just speeding up the molecules. Okay, so I'm going to stop here. We will do the next 3 on the next video. Thanks, guys.